Have you ever wondered what time dilation really is? If yes, this video is for you. Many physics students struggle with grasping the concept behind this topic while they're plunged right into solving its complicated mathematical equations. Trust us, we've been there, done that. Don't you worry, this video will not only help you solve the related formulae, but also help you understand what it actually means and how it's used in our everyday lives. That is, if GPS is what you regularly deal with. Hopefully by the end of this, you will be a little closer to Einstein's IQ. For starters, this concept may seem a bit ambiguous and somewhat non-intuitive, and you're probably asking yourself, time dilates? Isn't it supposed to be absolute? The answer is no. Simply put, time is relative, which means that it's experienced differently by different observers depending on their point of view. It's affected by two factors, mass and velocity. So to a stationary observer, a clock that is traveling at a speed closer to that of light, or situated near an object of significant mass such as a black hole, will appear to tick slower than one that is stationary or near an object of significantly lower mass like our Earth. This can be illustrated via this thought experiment. Imagine two twins who are exactly the same age. One of them hops in a spaceship and flies around the Earth at a high speed. When he returns, he finds that his twin brother has aged more than him. Why does this happen? Shouldn't they both age at the same rate? Well, according to Einstein, they shouldn't. The twin in the spaceship was traveling at a high speed, which made time move slower for him. The same effect is observed near massive objects. This time, one of the twins gets on the spaceship and flies over to the nearest black hole. Since black holes are much more massive than the Earth, time passes slower there compared to time on Earth. So when he returns, he once again finds himself younger than his brother. This is all well and good, but is there actually any evidence to this mind-boggling phenomenon? Imagine a train moving at a constant velocity through Tottenham Court Road Station. John is on the train bouncing a ball, with Mary on the platform observing. From John's perspective, the ball is simply moving vertically up and down. However, Mary sees the ball move in a triangular path due to the train moving relative to her. Only one bounce is observed in the same amount of time by both parties, but the triangular path would be longer than the vertical path. And since speed is distance over time, Mary concludes that the ball is moving faster as the path covered, according to her, is longer. However, now imagine instead of bouncing ball, John is bouncing a light beam between two mirrors. It's important to remember that the speed of light is always constant no matter what. That's the second postulate of special relativity. John would see the light bounce up and down, and Mary would once more see the light move in a triangular path. However, this time, since time equals distance over speed, and as the speed of light is constant, the time taken for one bounce would be shorter for John, as the distance he observes is shorter too. If we imagine that one bounce of the light is equal to one tick of the clock, the principle that a clock ticks slower when moving compared to when it's stationary is clear. Now we'll showcase the conditions under which time dilation is evident. Just as any other trade, math has its own big box of tools. However, we only need to pick out a few in order to deal with time dilation problem. To begin with, we have what we call reference frames. A reference frame is a coordinate system with axes of time and position. Each individual object has its own reference frame because it allows us to describe a position and time of points relative to that body. Next, we have a special transformation matrix called the Lorentz. This we use to link two reference frames together, allowing us to measure an object's position and time relative to another. Inside the matrix, we have a boost factor term, which accounts for the relative velocity between two objects. In this particular problem, there is an observer standing on a stationary platform and a passenger is on a train that is moving away with a constant velocity v. Passenger's coordinates, according to the observer, are given by this general vector. Now, if we assess the situation in the passenger's frame of reference, his position coordinates are all 0, who's at the origin. We can use the Lorentz transformation to obtain the values of the passenger's position relative to the observer. The results obtained show that the boost factor is key. Looking at the time coordinates specifically, it's clear that for every unit of time that passes on the train, the corresponding length of time elapsed on the stationary platform will be that unit multiplied by gamma, the boost factor. We can see quite clearly by looking at the equation that gamma will always be value greater than 1. This means that the stationary observer will always observe a longer time, making time tick faster for him compared to the moving passenger, reiterating that moving clocks tick slower. If the relative velocity is small compared to the speed of light, the v over c squared element will be tiny, and in turn gamma will be approximately equal to 1, making the effect of time dilation very slight and therefore unnoticeable. As this is not observed in our day-to-day lives due to the speed of train being insignificant compared to the speed of light, you may think, I can't notice any of this, so it can't be that important, right? Wrong. Let's take GPS as an example. The GPS satellites orbit the Earth at a speed of approximately 14,000 kilometers an hour. In order to accurately determine the position of any object within Earth's atmosphere, the clocks on these satellites need to be in sync with the clocks on the ground to an accuracy of 20 to 30 nanoseconds. This level of accuracy is important because our distance from the satellite is determined by measuring how much time a radio signal takes to reach reaches from the satellite. However, because of the speed at which the satellites are moving with respect to Earth, time moves slower on board the satellite. Clocks on the satellite will eventually differ from the clocks on the ground by 1/1,000,000th of a second, which is not meeting the required accuracy. A satellite's speed is nothing compared to the speed of light, and this time offset is unimaginably minute, so it can't be that big a deal, right? Wrong again. If left unaccounted for, this will cause the satellite to transmit inaccurate information, causing our navigation systems which rely on GPS fail. Imagine what kind of an Uber journey that would be. Arguably, the most interesting implication of time dilation is the possibility of time travel. Imagine you now hop on a spaceship that can travel at 99.99 of the speed of light and whiz away into space. Since you're moving at such a high speed compared to everyone on Earth, time for you was going slower. So when you come back to Earth, say 10 years later, for everyone on Earth, a whopping 707 years would have passed. Can you imagine what the Earth would look like then? So why don't we regularly send astronauts into the future? Problem is, to accelerate a spaceship to speeds that high, we need enormous amount of energy, which we're still not sure how to obtain. Perhaps one day, time travel can become a practical reality, though not anytime soon. There you go, time dilation explained. To recap, time dilation is the concept of moving clocks taking slower. However, these clocks need to be moving at extremely fast speeds. The concept is not just theoretical, it's actually needed in order for GPS systems to function properly. Lorentz transformations are used to convert between two reference frames. Boost factor within them is key, and it shows that moving clocks indeed tick slower. We hope you're feeling a little more like Einstein now.